Welcome. Today is April 3rd. We're going to develop a way to rotate the axes when not an angle. We can find exact values using the unit circle developed way back in the beginning of the year. You do have an assignment located in our Google Classroom. It is a one problem. It's a nice summary of what we have been doing so far. It's entitled GPS rotation of axes number 1. Under the solutions section, I provided for you a number of checkpoints to make sure you can identify whether or not you are making a mistake. And if you cannot understand why you're making a mistake, as always, communicate with me via email or Google Classroom, any screenshots, and I will find that mistake for you. My encouragement and suggestion is that you write neatly. You take the time to write out additional steps. It seems that most of your mistakes you are making are due to simply losing track of numbers and negative signs. So here we go. I have been given an equation. I do recognize it as a conic. I cannot complete the square because of the xy term. So what I'll do is find an appropriate angle of rotation that will allow me to eliminate this xy term. I go straight to my formula. Cotangent of twice an angle is equal to a minus c over b. A is 4, B is -4, C itself is equal to 1. Plug those in where they belong. Calculate, and I'm feeling pretty good. But at this point in time, whoa, hold on 1 second. This particular values of x and y do not lead me to any angles identified in my unit circle, which are all going to be quadrantal angles, which means they're multiples of 90 degrees, or some variation of a 30, 60, 90, or 45, 45, 90. The old me, what would I have done? I would have sat there dumbfounded and given up because I have no idea what to do. However, you guys who have progressed this far in college trigonometry, very impressive from a teacher's point of view, you know that you could step back and think about what are some ways we can work around this. Let's go back to our understanding of what cotangent of an angle, it doesn't matter what I label this angle, it's just an angle, actually is. By definition, cotangent relates to an x and a y coordinate of a particular point on what we call R. So let's maybe draw on those axes once again to look at them. There is my y-axis. There is my x-axis. Clean them up a little. I know that my cotangent, inverse cotangent, is defined in quadrants 1 and 2. Since this is negative, I must be in quadrant 2. So I think I'm going to just draw in my nice value of R. There it is. Where it is in quadrant 2 is not really relevant. I'm then going to draw my point P on this R value. There it is. And most importantly, I'm going to recognize what I've deduced, which is x and y, which is nice. This point P has coordinates. So let's figure out what those coordinates are. Since I am in quadrant 2, this negative sign applies to the x coordinate, not the y coordinate. So x must be -3 and y must be 4. Nice. Except for my notational error. Quick fix right there. There we go. Using Pythagorean theorem, of course, recognizing x squared plus y squared equals r squared, I should be able to calculate that r itself is equal to 5. Very nicely done. Now, why does it matter? Well, what matters is that I've identified where this angle is. I just have no idea exactly what this angle is. But more importantly, I've identified what is necessary to calculate any particular trigonometric value of this angle. And I do that. Specifically, I do it for cosine. Now, why I did it for cosine is yet to be determined, but cosine is defined as x over r, and there we go. Now, why do I care so much about cosine? Well, if you remember from the unit on trigonometric identities, there are two identities that we didn't do many calculations with, but nonetheless are going to give us some sense of purpose right now. They're called the half angle identities. Notice that half of twice an angle is a single angle, which is good to know because for my rotation values, I need to know the sine of theta and the cosine of theta. Also recognize that both identities just require the cosine of twice theta, which you and I figured out from the previous slide is equal to -3/5. What I don't know is whether or not it is positive or negative. So let us go back to the Cartesian plane. Inverse cotangent is defined from here to there, essentially 0 to 180 degrees, exclusive. Let me just remind you of that with a particular arc. There it is. When I take of the half of any particular angle from 0 to 90, half of 0, 0, half of 90 is 45. So that would lead me to get any sort of angle that is from 0 to 45. When I talk about quadrant 2, half of 90 is 45, half of 180 is 90. So that would lead me to this other top part right here. What is the moral point of my story here? Well, whether angle is from 0 to 180, half of it will always land me into quadrant 1, which means in quadrant 1, the sine value is always positive. So I've identified whether it's positive or negative. The cosine value in quadrant 1 is also always positive. What I would hate for you guys to do is think that this just magically disappears. It does not. We deduce and observe, and due to the laws of trigonometry, we're allowed to make conclusions. So you might have seen in your textbook or in future slides that I've already dropped the plus minus sign. It's because in this particular case, I've recognized that the values will always be positive. Make sure you understand that. Moving on. Now, while we recognize that we still do not know the measurement of twice theta, other in this case it is in quadrant 2, nor theta itself, which in this case we now know is in quadrant 1, we do know that the cosine of twice theta is -3/5, and we have half angle identities, which once again we've deduced both sine and cosine are going to be positive because we're always going to be in quadrant 1. Let's just do some trigonometry, or in this case some algebra. So I'm going to plug in the appropriate value of the cosine of twice theta. It's -3/5. 5/5 take away -3/5 would of course land me at 8/5. If I have 8 of something and I divide that in half, that will lead me to 4 of something. So that's the square root of 4/5. The square root of 4 is 2. The square root of 5 is the square root of 5. I then rationalize that, and I end up with 2 root 5 over 5. Down here, the cosine of theta is equal to this particular value. Once again, I figured out since I'm going to end up in quadrant 1, it must be positive. I'm going to use substitution. Square root of 1 plus the quantity of -3/5, 5/5 plus -3/5 is 2/5. So that leads me to there. And half of 2/5 would be 1/5. So that leads me to there. Square root of 1 is 1, square root of 5 is square root of 5. Rationalize that, and that leads me to the square root of 5/5. So what have I done? Without actually ever finding the value of theta nor twice theta, I nonetheless have been able to use identities to find the exact trigonometric values of the sine of theta and cosine of theta. And I remind you, these are the numbers we need for the purpose of the rotation formulas. There's my rotation formulas. Now let's just plug in numbers appropriately. There we go. Once again, this term and that term, I do see a common factor of the square root of 5 over 5. So I like to clean up my equation always and get rid of that. I'd encourage you guys to do that. Also, it just allows me to maybe deal less with fractions and radicals. Same thing over here. Putting in the appropriate values right where they belong according to the rotation formula that you and I figured out. Cleaning this up a little with algebra because I know I have a lot of calculations coming my way. When I take those two terms right there and I plug them all the way back into this particular, this particular equation right there. We are not going to take the time to do that today. You should already be able to do that. Our goal today was just to show how half-angle identities can be used to find exact trigonometric values for the purpose of rotating the axes. Make sure you know how to do that. The last thing I would like to point out to you guys, without a doubt, is that we now have rotation formulas. We're good. Quick summary of everything we've talked about with rotation of axes. Number one, I use it when I cannot avoid dealing with an XY term algebraically. Number two, you always must find the angle of rotation. The cotangent of twice theta is equal to A minus C over B. If theta comes from the unit circle, well, then you're rocking and rolling. If theta does not come from the unit circle, we are going to use the half-angle identities to come up with the cosine of theta and the sine of theta. Once again, we figured out that it will always be positive. You then are able to take those two and identify the appropriate rotation formulas by plugging in the trigonometric values. And then you're going to plug in the rotation formulas, eliminate the XY term, and complete the square. The last week and a half has been developing this playbook right here. And that is the end of our unit of rotation of axes. Make sure you take a screenshot. Anybody who has identified all of these in your notes, great job taking notes. And we will end our section of rotation of axes with a wonderfully challenging GPS problem in the future. Have a great day.